Okay, so continuity is a term that we use to talk about if the graph is continuous. Could you take a pencil or a stylus, put it on the graph? Here, there's like a little picture below. Could you put it on the graph and trace the entire graph without having to pick up your stylus or pencil? So if so, then it would be continuous. So things that would make a graph not continuous, here's 3 examples of things that can make a graph not continuous, would be the first one that I come to if x equals c1. What thing is that? First thing I came to. There's a hole. Okay, so I would have to pick up my pencil and then skip that hole and start again. So if we have a hole, then that would make it not continuous. That hole would be where C1, f of C1 is not defined. There could be, so after I pass C1 and I get to C2, I would have to pick up my stylus to jump down to here before I start tracing again. So at C2, what's the problem? Why is it not continuous? It's called a break. There's a break in the graph. There's a jump in the graph. Okay. And then the third one, we are tracing, and then we have to go down here, and then we have to come back up again. So this one is number 3. It's described as the limit from the left and the limit from the right are equal to each other, but if I actually plugged in C3, I would not get what the limits are. So the limits are not equal to actually plugging in C3. So at these 3 situations, the graph would not be continuous. Now, if we have a graph, it's really easy to tell. If we don't have a graph, then we have to rely on things that we've learned or things we are learning. So a definition of continuity has to check off these 3 things. So if you plug in a point, it's going to be continuous at that point if you plug in that point and it is defined. You don't get a 0 in the denominator. If the limit as x approaches c exists. So it would not exist if there was a break, right? Just like you did in the last assignment, would not exist if there's a break. And then also, if you find the limit as it approaches c, would be exactly the same as just plugging in c. So all 3 things need to happen for it to be continuous at that point c. And then if f is continuous at every point in that interval from a to b, then it is continuous on the interval ab. So that's how you would say it, just vocabulary-wise. Bold, okay? And then I already told you about that part. So continuity of polynomial and rational functions. Number 1, if it's a polynomial function, it is continuous at every real number. Polynomials continuous at every real number. So question A, f of x equals x squared minus 2x plus 3. It's a polynomial, so what can you tell me about its continuity? It's continuous at every real number. So this is how the book wrote it. They said polynomials are, I'm going to put it in a different color, continuous on the entire real line. That's how they worded it. But if we were just having a discussion, we would say they're continuous the whole time. No discontinuities. And so question B is also a polynomial, so it has the exact same answer. Number 2 above says a rational function is continuous at every number in its domain. So rational function, those are the ones that have a polynomial on top and polynomial on the bottom. Continuous at every number in its domain. So here's some examples of rational functions. And the first one, let's discuss the continuity of the first one. Can anybody tell me something about the first one? X can't be 0, exactly. So I'll just go ahead and make a note about that. X can't be 0, but that's not discussing the continuity. That's discussing what it can't be. So okay. Right, so it's going to be everything except for 0. So to write that, we'll just write that it is continuous on the interval negative infinity to 0, union 0 to infinity. So that's exactly what Christopher just said. Everything except for 0. Okay. How about B? So we should know that X does not equal 1 for the domain. But what can we say about its continuity? Who has an idea? Sam. Can you help me write the domain? Continuous on the interval. Hold on a second. I'm not right there. On the interval. Perfect. Thank you, Sam. All right, question C. Let's talk about its continuity. Is there something X cannot equal? Is there something that's not in the domain? So I hear no, I see nods yes. I? Is that what you said, I? What's I? Not real? So we're not going to talk about the imaginaries. We're just talking about the reals. So if it's an imaginary number that's not in the domain, that's okay. So what real numbers aren't in the domain? We're all good, aren't we? So this is continuous. Continuous on the entire real line. That's how they worded it in the book. I just copied what they said. Okay, the next paragraph talks about some more vocabulary words. So we've got a function is continuous at every number in an open interval except C. Then C is a discontinuity of the function. So it is, the discontinuity would be that one number that it kind of skips over. Discontinuities fall into two categories, removable and non-removable. So it is removable discontinuity if it is a whole. Okay. It is non-removable if there's something like a jump or a break or an asymptote. Yes. Are you talking about removable or non-removable? Or are you talking about discontinuity? What are you talking about? About going?
Is it non-removable?
Oh, non-removable. That would be, yeah, if there's a break.
No, like the graph goes in the same direction. It's approaching the same point, kind of, so that be removable or non-removable.
You're talking about the limit.
Yes.
Is that what you're talking about? Okay, so like, well, it depends. If it's like this, and we're approaching and we're approaching a hole like that, and they're approaching the same ones, this would be removable. If it was like one of those rational ones where they're getting closer and closer to this line, but what we're looking at is the y values, so they're going to different values, so that's non-removable. A removable one, they say that you could, if you wanted to, like, I don't have an example right now, but let's say with this graph right here, we could define it. We could like have an added information if we wanted to, say f of 1 equals 2 is something what they wrote, and then you could like color that in and make it continuous. So that's something that I can fix, where I can't fix like a break. I can't like connect those all of a sudden without changing the entire first equation. Yes, dear.
What I was saying was, if that fractional equation you drew, if they're approaching the same y value, if they're both going to infinity, how do you classify that?
So if they're both going to positive infinity, right? Is that what you're saying? Let me get back to you, because that's not in here. So let me find out which one it is. Okay? Okay. I think it's non-removable, but I don't want to say and then be wrong. So I'll look at it and make sure I find out for you, okay? So there's also continuity on a closed interval. So you might not be looking at the entire graph, but you might be looking at a particular interval of the graph, okay, of the coordinate plane. And you can also use one-sided limits to discuss this continuity, like what we were learning about last class. I forget what this one is. It can be defined on a closed interval where it starts at A, ends at B, if on the open interval, one side from the, from the right approaches, if you plug in A and I'm saying it wrong, sorry. If it's continuous from the right, continuous from the left, you can say that it is continuous within this particular interval. That's what it's trying to say. Like, you don't have to look at the entire thing. If we want to specifically look at, I feel like I need to draw this. Like A would be here and B would be here. So if we're looking at A from the right, then we're looking A going this direction if it's continuous, B from the left, so it would be like look in that direction. So we can say from here to here it would be continuous if we need that. There's also like half open intervals where it could be continuous from like starting point, but not quite equaling the ending point. So it would have an open dot at the ends. This example, we would be discussing the continuity of square root of 3 minus x. And you wouldn't say that it's continuous because there isn't a graph to the right of 3. So you wouldn't just like say it's continuous. You would specify that it has continuity within a interval. So looking at this graph, what interval would we say it's continuous with? Or on, sorry, on. Gavin, can you tell me? Negative infinity to 3. And then that would be half open. Sorry, I wanted to make sure I was saying the right word. Negative infinity to 3, because it does include 3, but it can't include negative infinity. So here's continuity on a closed interval. So we are looking specifically at the interval from -1 to 3. And we want to discuss the continuity from -1 to 3. Now, I put the graph there, but the graph is really not supposed to be there. But I didn't want to have to draw it after we talked about it, so it's there, okay? Let's pretend the graph isn't there. We want to talk about just from -1 to 3. If there's continuity, we have two different pieces. So if we cover up that graph and we've never seen it before, what do we need to know about these two pieces when we talk about continuity? Do they connect? Right. So we want to test the point, or we want to find the limit, and the point that we want to use is that connection point. So we'll do the limit as x approaches 2, and then we'll do it from the left, and then we'll do the limit as x approaches 2 from the right. And if I'm going from the left, I'm going to use 5 minus x. And if I'm going for the right, I'm going to use x squared minus 1. So I'll just plug in 2 because it's not going to make it undefined or anything. So we'll have 5 minus 2, which is 3. This one here, I'll have 4 minus 1, which is 3. So we have the same answer. So we can say that it is continuous. Individually, they're polynomials. So we know the individual pieces are continuous because they're polynomials. But since they both have, when I plug that number in, they both have that same, what's it called? Same limit, then the limit exists. And it is closed there because this one is closed. So it equals 3 at this one. And then it's, you know, I should have done this. It equals 3 here, but it's open here. So it does fill it in. It's not like they're both open and there's a dot somewhere else. One fills the other. So we know that they're closed. The greatest integer function. So you're going to answer some questions about the continuity with these. And we did this like so long ago, chapter 1. The greatest integer function, also called step functions, you kind of truncate the number that's in there. So if I do the greatest integer function, if I do like 6.32, you would tell me the greatest integer that is less or equal to 6.32. So what is the greatest integer, Eden? What is the greatest integer that is less than 6.32? Yeah, 6. And then I could give you one that's like negative 2.49. And we would say the greatest integer that is less than or equal to negative 2.49, Ryan. Negative 3 would be correct. Or I could do the greatest integer that is less than or equal to 10. And Barry, what is the greatest integer less than or equal to 10? It is 10 because it's already an integer, right? So that's how we evaluate those. And you can tell right here from the graph that we are going to have breaks. So it's not continuous. It would only be continuous in certain intervals for this, okay? This next one, we don't have to write anything or work anything out. It's just going through and showing you some other greatest integer functions that we haven't done yet. So this one comes with a word problem. A book binding company produces 10,000 books in an 8-hour shift. The fixed cost per shift is $5,000. So if they make 8,000 books in an 8-hour shift, it costs them $5,000. Plus, it's going to cost $3 per book that they made. Okay? Now, if they made 9,999 books, they're still going to get charged for that 8-hour shift. So it's still going to cost $5,000 plus, and then it's going to be a little bit less, $3 per book. There's going to be less books. If they only make one book, they're still going to get charged that $5,000 for using the 8-hour shift, plus just $1 or 1 times $3 for the book. So this is a step function because, or a greatest integer function, because anything from 1 to 10,000 is going to, within the first 8-hour shift, is going to cost that $5,000. So if they made 10,001 books, they can't do that in an 8-hour shift. They would have to have 2 8-hour shifts. So right here, this is what they're talking about. During the first 8-hour shift, we would use the greatest integer function where any number that I plug in here is going to equal 0. And then during the second hour shift, any number that I plug in here is going to equal 1. So if it equals 0 or if it equals 1, oh, they didn't show that part. Like right here, if it equals 0, you'd have inside the parenthesis, you'd have 5,000, 1 plus 0 plus 3x, which would give us 5,000 plus 3x. But if it equaled 2, or if this equals 1, we'd have 1 plus 1, which would be 2 $5,000 8-hour shifts. So we'd have 5,000 times 2 plus 3x. So that's where they're getting 10,000 plus 3x. And then you can see the graph. Because the cost of the book per book is varying depending on how many books they're doing, each of those little sections is a line, or well, a slanted line rather than a horizontal line, because it really matters how many books we produce. Does that make sense? Does anybody have any questions about this equation? You won't have to set it up yourself. I'm just going through how they graphed it. So if we were asking about the continuity of this, let's note the graph's continuities. How could we describe the continuities? Christopher, what do you think? Okay. Starting where? Just like 10,000, 20,000, 30,000. Is that what we mean by multiple? Yeah. Really, to describe this, you wouldn't be able to do this all in just writing like interval notation because there's so many of them. But possibly we could come up with some sort of formula. I want to see how they wrote their answer. I didn't look at the answer key yet, so I don't even know how they're writing their answer. I'm going to look at it real fast. They like didn't write any examples of how they're writing their continuity in the examples. They don't have any examples in the example. They didn't write it at all. So I'm going to check real fast. So this 27 is one that is a step function. And they wrote C to C plus 1. Now, you don't know what the equation is. But it does look like they're writing some sort of interval from the x to the x. But it says continuous on all intervals where C is an integer. So how could we do something like that? How could we do something like that? Yes, Christopher? So how could we write like the interval without multiple variables? Is there a way to write it without multiple variables? I mean, like our first interval would go from 0 to 10,000. And then we'd have 10,000 to 20,000. Is Christopher the only person that can do thinking in here? Is he the only one that is saying something? You're confused about what, hon?
I just don't understand. I don't know.
What part?
I don't know what it's asking for the C to C.
Oh, like, well, you didn't know what the question is, so.
That doesn't make any sense. I don't know if anyone else does the same.
Well, you're not seeing the question for that one. So you don't really know, like, okay, let me go up here. Let me go up to this one, okay? So for this graph, our intervals would be, I can't list all of them, okay? So I'll have like a union, ... that way. We could do -1 to 0. We'd have 0 to 1. We'd have 1 to 2. We have 2 to 3. Okay, those would be our intervals where we've got our break in the graph. Do you understand or not? So those, but I'm not going to write all of them because there's infinitely many of them. So if I have, yeah, but they use C. They use C. So C and then C plus 1, but you just have to say that C is an integer.
Yeah. Okay.
So now with this one, we're not going to have negative numbers for this. So maybe we say C is a positive integer, first of all. Can we have part of a book? Well, I guess. Are they, I guess my question is, are they going to pay for, maybe they have to pay part. I would think if they made a book, they would pay for even if they only made half the book, they'd still have to pay for the whole book. So now I'm like wondering why it's even connected in the first place. So technically it shouldn't even be connected. Oh, I'm thinking real life, like I wouldn't make 3/4 of a book and pay 3/4 times $3. I'm thinking about this situation. It's like $3 per book. Do you guys understand what I'm talking about? I'm like thinking that this shouldn't even be lines. Well, there's paper. There's paper for books, right? And a company needs to pay for the paper. And the more books they make, the more it's going to cost them to pay for that paper. No, you're paying for the usage of the machine to make the books. So you've got this set machine cost plus maybe people to run the machine. Maybe that $5,000 includes the people that run the machine. So you have this $5,000 per 8-hour shift. Plus you need the materials. But if we make less books, you don't have to pay as much for materials because we don't have as many books. So that 3x is a separate cost than just renting the machine and paying people. So there's the money to make it run, and then there's the money to pay for your materials. And that money to pay for the materials is what's making the line look slanted rather than horizontal, which is what we've only seen before. Okay, so now what I was saying is, I don't totally love their graph because I think I'm going too deeply into it, is because I feel like it should just be integers the whole time. And there really shouldn't be continuities. There shouldn't be intervals of continuity because you don't make part of a book. So hopefully they don't charge you for part of a book, right? So now I don't even like this question anymore. So I'm going to stop doing this part. Do we understand this one? Because the questions in the homework are going to be more like this one. Do we understand why C is an integer? It's going to go from C to 1 more than C. Do we understand that one?
So what percent?
So if I had, oops, I didn't mean to draw it through that. If I had a different picture and the graph was jumping up and we had like -1 to 1 union, 1 to 3 union, 3 to 5 union. If we had something like that, we could start by, we could start by saying C. But then what would the next thing be? Oh, C plus 2. Yeah. Sorry, I had to think for a second. C plus 2. So it's just with our first number, what do we do that first number to get the other one? That's kind of what they're looking at. Okay. I think I was making it too hard and trying to do that one where I don't even like the continuity of that. Okay. So that's really all you guys are going to be doing today is I don't remember what the start number is, maybe 5 to 43. I can't remember. Odd. And almost every single question is just find the continuity. Discuss find the intervals at which the function is continuous. And then a couple of them are discuss the continuity. And then there's a couple sketch the graph and describe the intervals of where it's continuous. But the majority is just write the intervals. Okay? So